Thank you for joining. Conrad, that was a very interesting presentation. Thank you. My name is Amelija, and I will be presenting our research about quantifying complexity, 3D printed concrete elements, also on behalf of Raitis, Pekuss, and Borja, García, Soto. We've chosen this topic because one of the biggest advantages of 3D concrete printing is the ability to create very unique free-form shapes that are extremely hard to achieve with traditional construction methods. Even with simple shapes, far more costs are significant, and it is also very time-consuming. 3D concrete printing provides an alternative to this, and in addition allows for the benefit of increased element complexity. But as you can already tell by me trying to describe such shapes, at the moment it is very difficult to evaluate all these different designs, to describe them and compare them in an objective way. Most often, only words such as complex, double curved, and geometric freedom are used, but these, of course, are very dependent on the viewer's interpretation. A quantitative measure of complexity would be useful for comparing productivity of different production methods, tracking the progress and development of 3D concrete printing technology, and more. For this reason, what we did in this study was establish two coefficients: intrinsic complexity coefficient, further on referred to as the ICC, and fabrication-specific complexity coefficient, further on referred to as the Fscc. We also designed and modeled 10 example pillars that you can see on the right with varied complexity on which we tested how the coefficients perform. Finally, we also used the ICC in productivity analysis. So the intrinsic complexity coefficient is only dependent on the shape of the object. It is obtained by considering the local geometries, specifically their curvature and variety. To calculate the coefficient, we use the mean curvature as well as the shape index, which is a non-dimensional and scale invariant coefficient in the range -1 to 1. The lower end of the range, which is -1, represents a spherical cup, while the higher, which is 1, a spherical cap. The shapes in between the two limit values vary, representing shapes such as rut, saddle, ridge, dome, and etc. Here is the general procedure for obtaining the ICC. If we explain it briefly, to get the ICC, we select equally spaced points on the surface of the element, and for each point we calculate the mean curvature and the shape index. Then we group the values of shape index into certain ranges, which informs us about the variation in the local geometries. To evaluate the local geometries, we use the mean curvature. I think the main takeaway should be that the main factors that affect the coefficient are the mean curvature of local geometries and how varied they are. The Fscc is different from the ICC because the value of the coefficient is no longer only dependent on the design of the object. The coefficient considers the context of how an element is fabricated, which is material properties, printer properties, and the design. It can be used to evaluate how difficult it would be to print a specific object with specific tools and materials, and to compare which objects would be easier to fabricate in a certain facility, for example. Again, here is the general procedure. There are two main tasks for obtaining the Fscc. First is running the buckling simulation provided by Vitamin and Boss, Karamba 3D, Nanyang Technological University, and TU Eindhoven. In the simulation, you input all the material properties, printing settings, and the design, and the simulation returns the value of how high the element can be printed before it buckles. The remaining height we express as % of total height of the object to obtain the variable b, which we call ease of printing. The second task is to obtain the resolution. Similarly to a picture, we define the resolution by how close the printed element will be to the actual model. Thus, we quantify it as the % difference in volume between the printed element, which is sliced, for example, in 1 centimeter layers, and the actual computer model. An illustration can be seen in the picture showing on the right, which shows concrete mist in red and printed extra in green if sliced in 4 centimeter layers for pillar 10. This is compared to the original model. This value we obtained through a specific Grasshopper code that we created. And lastly, we have the productivity analysis. We're arguing that when producing more complex elements or elements with a higher ICC, the process is more productive, as in this time, a more complex design is achieved than, for example, a circular column. For this, we introduced a scaling factor, F, that reduces the time to account for the added complexity. It is not meant to be a reflection of real-life production time, but a measure used for comparing productivity. So these are the example pillars. You can see both the side view, top view, and the associated numbering. The pillars were designed using Rhino 6 and Grasshopper, which was also used to obtain the resolution and other necessary variables for calculating the Fscc. For the results, we have calculated the ICC and Fscc for all 10 of the example pillars. The results show that the ICC and Fscc have an R-squared value of 0.6. Thus, they are not strongly correlated, yet they show a generally similar trend. This supports the idea that for 3D printing concrete elements, the shape and design of the element does not directly impact the difficulty of printing, which contrasts traditional methods where generally an increase in shape complexity results in increased difficulty in production, also leading to additional costs and time. This slide shows the distribution of shape index values for each example pillar. We can see that, for example, pillar 1, that is a regular circular column, has no variation in shape index because the surface is the same at every point, whereas pillar 10 has a lot of variation visible by all the indentations and varied design. We also calculated the variance of the shape index, and we can see that, as I mentioned earlier, it impacts the coefficient. The trend is similar with the ICC, except for pillars 5 and 6, where the variance is very low. However, because the mean curvature is very high for these pillars, in the end, we end up with comparable values for these pillars. I think these 3 graphs are a great illustration of the interplay between these 2 factors of the ICC. In this table, we have summarized the results for the Fscc, and you can also see the intermediary values for the ease of printing and resolution for each pillar. For example, for pillar 2, the resolution was 0.1 and height at failure 168 centimeters from 200 centimeters. So 32 centimeters were not reached, which is 0.16 of 200 centimeters, which gives us the value for ease of printing. Multiplying the resolution and ease of printing gives us a value for Fscc, which when rounded gives us 0.02. For the productivity analysis, we used some data from a productivity study by the co-authors of this paper. The study provided duration of construction for a similar size circular concrete column if constructed by in situ, precast, and 3D concrete printing methods. The ICC value for these columns was assumed to be the same as for pillar 1, which has the same circular shape. And for the printing time of the example pillars, we took 59 hours, which was the printing time provided by the paper for the 3D concrete printing method. After scaling, we can see that for some of the pillars with higher ICC values, they can be considered more productive to produce than those produced by in situ or precast methods. Overall, we believe that the coefficients are a good start in quantifying the complexity of concrete elements. Of course, there were several limitations to the study. First, the coefficients were created through observations and just general logical thinking. Thus, in the future, more variables could be added, or the weighing of the variables could be adjusted to make them more appropriate. Second, the coefficients are better suited for curved designs than ones with straight edges. This does align with how objects are generally designed for 3D concrete printing, but perhaps the coefficients should be more versatile. Third, only 10 elements are evaluated, which raises concerns of lack of statistical relevance. And lastly, for the productivity analysis, there were many assumptions made. So for more reliable results, we would encourage to do more precise testing and calculating ICC for each case. But overall, we think the study and the coefficients were successful and a good first step in quantifying the complexity of 3D concrete printing elements. Thank you for your attention.